Hey guys, I just wanted to give you a little bit more clarification and guidance in terms of completing your report, which consists of data sheets 1 and 2 on page 63 for colorimetric determination of aspirin. So if you take a look at data sheet 1 on page 63, that's preparation of standard solutions. But before you make standard solutions, I hope you understand that you have to make stock. So just to review, you're going to take about 0.4 grams of acetylsalicylic acid, or ASA as it is referred to in this experiment. You're going to heat it with sodium hydroxide. After heating and boiling is complete, you're going to carefully take the flask off of the hot plate using a hot mitt and keeping in mind that vapors may be produced. And then once the flask cools off, you're going to carefully transfer its contents into a 250 milliliter volumetric flask that looks like this, using a funnel, of course. Once you've transferred everything, don't forget to rinse the Erlenmeyer flask with a little bit of water, DI water, and put the rinses in here. That ensures that the entire sample is transferred. And then you're going to fill the flask to the mark. There's a mark of etched glass here, of course, on the volumetric flask. This is how you're going to fill it. So fill it quickly to about here, and then use a pipette or wash bottle or eyedropper to carefully, slowly add water so that the meniscus is right at the bottom of this mark. You will then cover the flask with a little bit of parafilm, stretch it over the mouth, create a cover, and invert the flask at least 10 times to mix the contents. This is going to be a stock solution. If you look at initial part of data sheet 1, it has you find moles of ASA based on mass that you weighed. And then for moles of ASA, you're going to go to molarity or molar concentration. Keep in mind that volume, molarity of course is moles over liters. And remember, for liters, you're going to have to use 0.25 liters because this is the volume of your flask here. So that's going to be your stock. And then you're going to take a portion of the stock and dilute it into, and transfer it first into 100 milliliter volumetric flask. As you can see, same shape, just different size, smaller flask. So the amount of stock will vary. As you can see, you have list of standards. We are going to be making only 4 standards, not 5. So we're going to be making standard A, B, C, and D. And we're going to omit E. And you're going to work with a partner. Now, typically you'll be working right next to each other, but because of the need for social distancing, the way I envision this happening is you're going to each prepare 2 solutions, and then for example, one of you will make A and B, and the other one will make C and D. And then once you made them, you're going to measure their absorbances and then basically share data with each other. This way, touching of the flasks and need for social distancing is preserved. I'd like to point out that all of the solutions, all 4, must be measured for absorbance using the same spectrometer. So make sure you coordinate with each other as to which spectrometer you're going to be using. There will be several set up around the lab. So just to kind of make sure everyone is on the same page, how do we find concentrations of standards? Just a reminder, we're going to, after transferring, say, 4 milliliters of stock solution into here, you're then going to add the yellow solution from the from the brown container, brown container in the hood to the mark here. And as soon as you start adding that yellow solution to your stock, it should turn purple because remember, phenol group will react with the FeCl3, producing purple complex. The difficulty you might have here is the fact that the solution is so dark in color that it's hard for you to see the bottom of the meniscus when filling the flask properly. Remember, volumetric flask is typically considered filled properly if bottom of the meniscus is touching the line. So for color solutions, there is a different rule, which says you fill the flask so top of the meniscus is across the line, not its bottom, because you simply cannot see the bottom of the meniscus. So you need to find molar concentration of this purple complex in this flask, and the formula you're going to use is the dilution formula, which should be familiar from Chem 1240. M1V1 are parameters, molarity and volume before dilution, while M2 and V2 are molarity and volume after dilution. So we're looking for molarity of standard after dilution has occurred, so we have to express M2. So we express M2 as M1V1 over V2. So how do we find all these parameters here for, say, solution A? Well, M1 is going to be equal to molarity of stock found up here, found previously. For solution A, you're going to use 4 milliliters of stock to transfer into 100 milliliter volumetric flask. So V1 will be 4.00 milliliters and V2 will be 100 milliliters, because V2 again is the total volume of this flask once you diluted the solution to the mark here. And then once you prepared for standards and measured their absorbances, there's also data sheet 2 that deals with finding amount of aspirin in a commercial medicine. What we will do is ETA will tell you which medicine each pair is supposed to test, and one of you will run one separate test. So you'll take a tablet, whole tablet without crushing or breaking it. You'll weigh it. It's fine if it's more than 0.4 grams. Some medicines, tablets weigh more than 0.4 grams. You're going to weigh a tablet. You're going to place the tablet, whole tablet, in the Erlenmeyer flask. You're going to add sodium hydroxide. You're going to heat, and then you're going to make same series of dilutions. First with water into larger flask, and then with yellow solution into this flask, and measure absorbance of this solution. And then this is going to be your unknown. So if you look in data sheet 2, where it says absorbance of solution, that's the solution that's purple in a smaller flask prepared from the tablet. You may skip percent transmittance. For both data sheet 1 and 2, there is entry for percent transmittance. We are not measuring percent transmittance, so you can skip it. And then from there it asks for concentration of aspirin in this solution made from the tablet. You cannot find this concentration until you use your data for standards to create a calibration graph. Once you get the calibration graph, which as we discussed should be linear with y-intercept equaling 0, which you can set it in Excel, set y-intercept to 0 for your graph, get the equation of the line, which will look like y, certain numerical value, x. So the computer calculates the line of best fit for you, and then using absorbance of your known solution prepared from the tablet, you plug in absorbance in for y, just to remind you. So absorbance is equal to epsilon times B times concentration. It's similar to y equals k times x. And so this here will be your slope, which the computer will calculate for you. So your concentration is what you need to find, so it's your x. So you will prepare the graph. The graph must have a title. We usually title the graph, as in science it's pretty strictly enforced. Usually the title should be representing, so you have your dependent variable here, which in our case is absorbance, and independent variable, which is concentration in moles per liter on x-axis. So in science, the titling is done by using dependent variable versus independent variable format. So in our case, it would be absorbance of purple complex or absorbance of ASA versus concentration. Make sure your graph has X is labeled, A is unitless, so no units here. For concentration, you must have moles per liter concentration. And usually it's advised that you specify concentration of what, so you would write concentration of ASA maybe here, specifying that you're measuring acetyl salicylic acid concentration. The graph, once again, should be best linear fit, not the line graph. So make a scatter plot, ask a computer for scatter plot first, and then ask for linear trend line. So you want scatter plot followed by linear trend line. And then once you have your linear trend line, something like this, don't forget once again to set y-intercept to 0. That's also possible to do in Excel. And ask the computer to show you equation of the line. The equation will be y equals certain numeric value x. That numeric value here, of course, is your slope, which of course, because b is equal to 1, as we discussed earlier, your slope will be equal to epsilon. So at the bottom of data sheet 1, it asks slope of Beer's law plot. That will be this numeric value here from your graph. And then underneath it says molar absorptivity. I hope I was able to get my point across, talking about it quite a bit in the previous video as well as in this one, because path length of light is fixed at 1 centimeter because of the width of our cuvette. Slope of the light is equal to epsilon. In other words, molar absorptivity and slope are numerically equal, so you will enter the same value for molar absorptivity as you entered for slope. And please keep close attention to units. Remember, molar absorptivity does have units shown here on your data sheet 1. So your report for this experiment will consist of data sheet 1, data sheet 2. You'll have only 2 determinations for data sheet 2 because each of the 2 partners will be able to do only 1 run or 1 determination, and then once again you will share data with each other on that. And so 3rd determination on data sheet 2 is not needed. One last comment I'd like to make is when you make your solution in here in this flask for the tablet, the complication is the tablet is a mixture of several ingredients, and so when you heat the tablet with an AOH and then pour the solution in here, that solution may not be colorless. It may be either yellowish or blue, depending on which medicine you are assigned. That is not a problem. It's not going to screw up your results. What you also need to be careful with, so if the solution happens to be colored, don't worry about it. It will still turn the same purple as before once you add yellow solution in here. One thing that you should sort of be concerned with and maybe consult with your TA is the fact that tablet contains starch binder to keep all the ingredients from falling apart. And starch is not soluble in water, and so this solution here may be cloudy. And if it's cloudy, the cloudiness will interfere with your absorbance measurements. It will cause you to have extremely high absorbance because light will scatter on the solid particles and will not reach the light detector, which will be read as high absorbance. So if the solution happens to be cloudy, like I said, consult with your TA. Usually it's possible to just let the solid particulate to settle and draw your sample from the upper part of the flask where it's not as cloudy, or if cloudiness is extremely difficult to get rid of, your TA might suggest running your solution through a piece of cotton, which will act as a filter and pick up all those particles to make your solution clear before you dilute it into the second flask. So hopefully all these directions will help you be successful in this experiment.